In this video, I'm going to demonstrate some exploration and experimentation that I've done recently on the topic of image classification. So just a very rough overview is uh, forming subclasses. So starting with a digit like 0 and the different samples that you have to demonstrate that digit and breaking it into subclasses and using those to create an improved classifier. So oftentimes I enjoy kind of experimenting with the simplest ideas to get a good intuition and building up from there with various ideas, just using it as a way to kind of explore and improve your understanding of the area rather than perhaps just reading kind of the literature. So the simplest possible classifier that I could imagine was taking all the different samples for a certain handwritten digit, finding their average, and then to classify, and doing this for all digits, and then to classify a particular handwritten digit, what you do is take the difference between your image that you're classifying and the various average digits and choosing the one that has the smallest difference. So in this case, it is correctly 1 that has the smallest difference between our particular digit and the average one. So that actually gives an overall accuracy of 81% on MNIST. This is just on the training set, not the test set. But it's intriguing to me that that can do that well with such a simple technique. Where I went from there is I was exploring a concept that I'm calling a correlation map here. I don't know what the proper term for it would be, but if you take the average 0 digit here and you choose a pixel that is roughly black in about 50% of images and white in 50% of images, you can ask yourself the question, you know, what is the kind of meaning or structure behind what would cause that digit to be black or white? Now, for a particular image, there could be a lot of different reasons, but kind of on the average. And so what I did is I constructed what I'm calling a correlation map. So this darkest pixel here is my target pixel, and then the color of any other pixel in the image is an indication of how likely that pixel being black increases or decreases the likelihood of my target pixel being black. So because of the symmetry of a 0, if these pixels over here are black, it actually increases the likelihood of my target being black. And likewise, there's an inverse correlation here, where if any of these guys are black, it actually decreases the likelihood that my target will be black. So I found this resulting image quite interesting. I wasn't expecting there to be these kind of, if you kind of look at it a certain way, there are two styles of 0 being shown here. The pink pixels represent a certain kind of style of 0, and the blue pixels also represent a certain style. So from there, my question was, well, if you took all of the images where that pixel is black and you averaged them, would you end up with an image that's kind of like this pink pattern? And if you took all the images where this pixel is white and averaged them, would you get a 0 that's kind of styled this way? So I ran that experiment, and it turns out the answer is yes. You get this kind of wider, more upright 0 and this more slanted, narrow 0. From there, my curiosity was, well, what if you did this repeatedly? What if you took this style of 0 and then you split it again by choosing one of the pixels that's roughly 50% likelihood to be white or black, and split it into another 2 subclasses, and likewise did it here? You could then form a kind of tree of subclasses. So I did that. What I'm showing here is 4 repeated splits that give you 16 subclasses of 0. And I just find it kind of interesting and not quite intuitive that you would end up with such kind of distinctive and well-defined subclasses. You know, you have very leany, very slanted 0s. You have zeros that have kind of a thicker stroke width. You have a very narrow and upright zero. This is kind of an egg-shaped zero, perfectly round zero. Just kind of interesting. So from there, my curiosity was, well, what if you built a classifier and rather than just having the average zero as the only thing you're comparing a new to be classified digit with, what if you took all of these subclasses and so you'd have 16 subclasses for 0, 16 subclasses for the digit 1, and so on for all the different digits. If you did that and then you chose, so now you'd have 160 kind of classes in total, and then you compared your new digit that you're trying to classify to all 160, chose the one that's best, and if that's a 0, you classify the thing as a 0, or if it's a 1, you classify it as a 1. How would that affect the overall accuracy of the classifier? Now, when I ran this experiment, I actually continued to split until I had 256 subclasses for all digits. So the results are that the accuracy went up from the original 81% to 96.8%. Again, this is on the training set, so it's a little bit overly optimistic. I think it was 95% when I tried it on a subset of the test set. But I just find that kind of an interesting result, that it would so dramatically increase the accuracy of the classifier. And overall, just kind of intriguing that this technique of choosing a 50-50 pixel and splitting the class results in such kind of coherent subclasses. So from here, 3 questions that might be interesting to further investigate are, I guess the first thing is, choosing 50-50 pixels is one way that you can create subclasses. What would other techniques be that might be more effective, and kind of what's the theory behind kind of techniques for this repeated splitting? Another question is execution time. So if you have 256 subclasses of a 0, then for all digits you've got 2,600 subclasses, and to do a classification, then you're doing a lot of image comparisons, and it's not really practical. So what would be ways of speeding that up? The most obvious is, because each of these subclasses in this case have 4 pixels that have a particular white or black value, you can take a new digit that you're going to classify and you can actually figure out with a very small computation which of these subclasses you might expect it to be closest to, and you could only compare that one, or you could only compare the ones that have a similar 4-pixel pattern. You'd expect that to affect your accuracy though, but it would be an interesting experiment. But more in general, are there ways to take this large set of subclasses and kind of compress them into a more compact representation? Maybe it's a hierarchical representation or something that would still give you a decent accuracy, but wouldn't require such a massive amount of computation time to do a single classification. The last question I think actually is the most interesting for me, just to revisit this idea of a correlation map. I find it quite interesting, the notion of what I would call a non-local correlation. We expect there to be what you would call local or adjacent correlations. You know, if one pixel in the image is black, it really increases the probability that an adjacent pixel is black. But if you see a non-local correlation, I guess what I'm sensing is that that's an indication of meaning. In the case of a 0, it's symbolic of the fact that zeros have a symmetry about them. And you know, you would also expect to see a correlation map show that if there's often a line in an image in a certain location, it should pick that kind of thing up. So it would be interesting to see whether you could use non-local correlations in a kind of clever way to build up a model of a class in a way that was really great for doing classifications or something. So more investigation is required there. But anyway, that's the result of these experiments, and I found them interesting.